Okay, let's start the second talk of this morning and also the last talk in this morning section. We are very happy to have Professor An Haipeng from Tsinghua University. He's going to talk about consequences of phase transitions occur during inflation.
Okay, thank you very much for the introduction, and I'm really happy to have this opportunity to present my work in this large conference. And so here's the titles, the title and yeah. So this work will be, this talk will be based on the works done with my collaborators and also some ongoing projects. Now let's start. So this is the picture of the Big Bang theory, and so we know that. So I think we all know the basic stories of thermal Big Bang, the history of our universe, and so basically the temperature keeps dropping down, right? And once the temperature drops below 0.3 eV, we know that recombination happens and our universe becomes transparent. And the light can just go through the universe and fly into our eyes. So that's the largest size of the universe we can see, which is the size of the cosmic microwave background, right? And people have done a lot of observations of the cosmic microwave background, just from the very beginning that we measure a thermal black body spectrum, which tells us that the temperature is about 2.7 Kelvin. And also later, people send out like satellites, telescopes to measure small structures, to measure more and more carefully about the cosmic microwave background, right? And so we just saw a lot of small-scale structures, although of these fluctuations of this cosmic microwave background. Although the fluctuations are super tiny, but they are there, they can tell us a lot about our universe, right? So one thing they can tell us about our universe is the following, right? So first of all, it is actually very strange that if you see the CMB from all the directions, the temperature are actually the same. And not the temperature are the same, but the fluctuations are also very, very similar, right? And we saw some very similar things. We should guess that they should have the common origin, right? They have some common origin means that they should have the same, right? So they must be causally connected to each other. Then people did this kind of interesting calculation based on the Big Bang theory, and we know that in the Big Bang expansion, the expansion is decelerating. And if the expansion is decelerating, that means in the past there is a singularity in our universe, right? In time, there's a singularity. So then we can just evolve light cone back into the singularity. And it turns out that once we did this kind of calculation, then the 2 points very far, 2 points on the CMB, if they are very far from each other, their past light cone just cannot intersect with each other, right? So that means in the standard Big Bang theory, they have no common past. That means there's no reason to believe that they have this. They should be the same, right? They should look similar. So that is a causality problem of the Big Bang theory. So we know that usually when we have a causality problem, and if we can solve this problem, we can make very big discoveries. For example, this Mr. Alfred Wegener, right? So we all know this from high school geology class, right? Geology class. So what he found is that he just looked at the map, and he see that the pattern of this of American continent is very similar to the Africa, right? To Africa and Europe, right? And then so he made this very bold guess that they should be the same continent in the past, right? And so people later found other evidences. For example, in Africa we have this ostrich, right? And in Africa we have ostrich. And also in Australia, we have this emu, right? And they look very similar. So they should have the common origin, right? And what will happen if they don't have some common origin? We know that this Australia continent, it was separated from the main continents a long time ago, right? So it should have enough time to develop its own animals. For example, all these animals developed from there with this broad pouch, right? With this broad pouch, for example, we have this koala and we have the kangaroos, right? They both have this one, and the animals from everywhere else doesn't have that. So we know that even you have a very small, very small disconnection, you will develop something very, very different, right? So that's actually tells us that because they look so similar, they should have some common origin. So that's why people have, and so in the case of in the case for Mr. Alfred Wegener, right? So he just so his guess was just correct, and later people had this developed this theory of the drift of the plates, right? Continental plates. And so all the continents were actually connected to each other to form this Pangea Ultima continent. Yes, and this is the same story for cosmology. So to solve this causality problem, I think everyone knows the story. So people just conjecture the theory of inflation. So what happened for inflation is that during inflation, it is assumed that the expansion of the universe was accelerating, right? And because the universe was accelerating, so there was no past singularity. And so we just connect the two together. So before the Big Bang thermal expansion of the universe, there was an inflation phase. And in the inflation phase, the expansion is accelerating. And for some reason, inflation stops, right? Inflation has an end, and all the energy density of the inflaton field just go into the standard model plasma, and then the expansion of the universe becomes decelerating. And if we can connect these two together, we can just solve this causality problem, right? So that is the main problem faced by the thermal Big Bang theory that can be solved by inflation. And inflation not only solved the causality problem, it also solved other problems. For example, the Big Bang universe also has the problems of flatness and also magnetic monopole problem. So inflation can solve all these three problems, and also as a byproduct, inflation can generate during inflation. The universe can just generate the quantum fluctuations, and that later becomes the seed of the large-scale structure, right? And through this seed of large-scale structure, people can just observe what happened during inflation. So that is actually a very important prediction from the inflation theory. But unfortunately, to solve all these problems, the inflation should last about 40 to 60 efforts. So what does this mean? This means during inflation, for example, if it's 60 efforts, that means inflation, the expansion of the universe should be something like e to the 60 power. Okay, so that is actually very large. And so, as I just said, through these fluctuations of our universe, we can observe the information of inflation, right? And so, however, if we combine all the things we can observe, we can observe the fluctuations through CMB observation, right? And also the Lyman alpha surveys and also other kind of large-scale structure surveys. But if we put them together, it's only about 10 efforts. So that means a large part of inflation is actually unknown, okay? So, and another fact is that currently the most successful inflation model is actually the slow-roll inflation model. So what is the slow-roll inflation model? Slow-roll inflation model means that we assume that during inflation there is a scalar field, and most of the energy density, most of the energy in our universe is actually stored in the potential energy of this inflaton field, and the potential of the inflaton field is actually very, very flat, right? Because it's very flat, then the rolling of the inflaton field is actually very, very slow. So that means for a very long time, we can assume that the potential energy is actually a constant. And if that is a constant, it can work as the cosmological constant, right? And it can have an exponential expansion of our universe. So in that case, we know that currently the universe is dominated by dark energy, and the expansion is accelerating, right? And so this is the mechanism, the similar mechanism for inflation. And so all the energies are stored in the almost constant potential energy, so that the expansion is accelerating, right? And so after a while, when the rolling of when the inflation field come to the bottom of the potential while, then then the inflation stops, and then during this oscillation phase of the inflation field, it can decay into the standard model field, and so then it just released its energy into the standard model plasma, right? So that is the basic picture for inflation, and so, but if we want a successful inflation model, what will happen is also the following. This is also the fact that if we want 40 to 60 efforts of inflation, the excursion of the inflation field during inflation should be very, very large. Right? So how large is that? We know that the largest scale in our universe is the Planck, right? And it turns out that to have a successful inflation model, the excursion of the inflation field during inflation should be as large as the Planck scale. And in some model, it is even larger than the Planck scale, right? So that is that might be a problem, but that may give us something good, right? So we can just take advantage of this large field, this large excursion of the inflation field to do something, right? So that is actually that is actually the motivation of our work in this talk. So yeah, okay. So this is let's review what are the facts, right? To have a summary. So to solve to solve all these problems, what we need is 40 to 60 efforts inflation, but we can observe it's only 10, right? So that means in the rest of the time, a lot of things can happen. Yeah, and we also know that during inflation, the excursion is very large. But what we can observe is actually only a very small part of this inflating potential, right? We know that in that part it should be flat, right? But for other parts, we actually don't know, okay? We actually don't know what happened in the rest part. It can be just like this. It has a lot of wiggles, but we don't know what really happened. And another fact is that the inflating field must couple to some other field, so that at the end of the inflation, the inflating field will the energy of the inflating field will be converted into the energy density of other fields, so that inflation will end and our universe will go into the standard Big Bang theory, right? And so we can have some examples, give some examples. So we assume that, so during this talk, phi is the inflating field and sigma is the spectator field. We can assume there are some interactions between them, right? For example, we can write down a direct interaction, the phi square and the sigma square, okay? Sigma is the spectator field and phi is the inflating field. And so what happens is that during inflation, the change of the inflating field is as large as the Planck scale, right? So that means the mass square of the sigma field will also change a lot. And that might flip sign of the mass square of the sigma field, and that will give us a phase transition, right? And the second example is like this. So we can write down an interaction between the between the inflating field and the Yang-Mills theory, okay? Just like Professor Wang talked. So a Yang-Mills theory. And then during inflation, what happened is that because phi changes a lot, so then this Yang-Mills theory may just go from a weakly interacting regime to a strongly interacting regime, right? If that happened, that means a phase transition happened, right? And so in both cases we have phase transitions induced by the evolution of the inflating field. So this is the strategy of our work. So we assume that during inflation, the evolution of the inflating field trigger a phase transition in the spectator sector. And what we want to study is the phenomenological consequences of this phase transition. So what it will induce? So first of all, if the phase transition is first order, it will generate bubbles. And the bubble will collide with each other, and that will produce gravitational waves, right? So this is what we call the primary gravitational wave. And if the phase transition is symmetry restoration, then the particles created during the phase transition, during the bubble collision, can be stable, and that can give us the dark matter candidate. Okay, and if the phase transition is symmetry breaking, that will give us topological defects. So what I will show is that the topological defects will also produce gravitational waves that can be observed today. And also, because we assume there's a phase transition happening in the spectator sector, and because there's an interaction between the spectator sector and the inflaton field, right? And so that means that the phase transition of the spectator sector will give a back reaction to the inflaton field, and that will generate a curvature perturbation. And the curvature perturbation, if it is large enough, it can produce primordial black holes, okay? And it can also generate the large-scale structures. And also, once all these curvature perturbations re-enter the horizon, it will produce secondary gravitational waves. And what I will show is that this secondary gravitational wave can be very important, and it might be it might be the source for the signals observed by all the pulsar timing array experiments last year. Yes. Why? Because inflation must have an end, right? So that means the inflaton field must couple to some other field. So that after inflation, it can transfer its energy into other field. So in general, there should be something coupled to the inflaton field, right? Yeah. So that is one of them will be our spectator field. So this is a very general assumption. Okay, so this is the outline of my talk. So I will first focus on the first order phase transitions during inflation, and I will start with the properties of the primary gravitational waves and dark matter and curvature perturbation, and secondary gravitational waves and primordial black holes. And then I will focus on second order phase transition. And for second order phase transition, we know that usually we cannot directly produce a lot of gravitational waves. But then what I will show is that through topological defects, and I will focus on domain walls, so that will give us like large enough gravitational waves. And then I will summarize and give some outlook. So that starts with the first order phase transition during inflation. So phase transition, right? So what is phase transition? We all know that through everyday life we have phase transitions. For example, we boil water, right? And there will be bubbles inside the water, and when bubbles collide, and the bubbles are made of steam, and when the bubbles collide with each other, we hear the sound, right? And here in the early universe, it's the same. So we also create the first order phase transition also create a lot of bubbles, and when the bubbles collide with each other, it can produce gravitational waves. So just like the sound wave, right? And so usually, if we can have first order phase transition, that means we have two vacuums. One is the true vacuum, and the other is the false vacuum. And so for first order phase transition to happen, we can assume that. So in our case, we have an inflaton field phi, right? So this phase transition is not triggered by the change of temperature, but it's triggered by the change of the inflaton field. You can see that this V1 is actually a potential of the sigma field. And once we have different values for phi, the shape of the potential actually changes, right? And so you can see there's a bump, the potential bump between the true vacuum and the false vacuum. And with the evolution of the phi of the inflaton field, this barrier becomes smaller and smaller, right? And when this barrier becomes smaller and smaller, there's a bounce action that the bounce action actually determines how hard the tunneling can happen, right? And once this barrier becomes smaller and smaller, it is easier and easier for the tunneling to happen, and it is easier and easier to have the phase transition. And once this bounce action is small enough, then the phase transition can just complete. And what determines the rate of the phase transition is actually this beta, right? We know that a rate must be something has a dimension 1, right? And this rate is just defined as minus ds4 over dt, and s4 is the action for the bounce, okay? And it is this value of beta that determines the rate of the phase transition, and also it determines the size, the typical size of the bubble, and also the time scale of the phase transition. For example, we can do some simple numerical simulations. And also for the phase transition to complete during inflation, we must require that beta should be much, much larger than h, right? And we know that this can always happen because just during the phase transition, when this bump will eventually disappear, right? And that means this beta will eventually diverge. So at some point, this beta must be much larger than h for the phase transition to complete. So that means for this kind of phase transition, it can always complete during inflation. And so here we can do some simulations. So this is a very simple numerical simulations to see that this value of beta actually determines the time scale of the phase transition. So this y-axis here in this x-axis is actually the time, the physical time in the unit of h inverse, and h is the Hubble, and the y-axis is the fraction of the true vacuum. And you can see that we can choose different values of beta over h. And also, as you can see that once beta over h becomes larger, it takes a shorter time for the phase transition to complete. Okay, so once the fraction is almost 1, then we know that the phase transition completes. So, yes, the height, this one. This is the fraction of the, yeah, so the y-axis is the fraction of the new vacuum, of the true vacuum. Okay, if the fraction is 1, that means it's completely true vacuum, and if 0 is a completely false vacuum, right? And so we can, yeah. So this is the meaning of the height, yeah. And you can see that the phase transition can actually, it actually finishes very faster with a larger beta. Okay, yes. Calculate the rate. That's the rate of the phase transition, right? We know that the rate, it is actually counted by gamma over v, and gamma is the tunneling rate. It is the bubble nucleation rate per volume, right? And so that is that value always proportional to something like m to the fourth times e to the minus s, right? And m is the typical energy scale of this spectator sector, and s is the bound section. And for s, we can simulate it using some kind of software, for example, calculations. Yeah. Yeah, this is common method. Oh yes, but yeah. So the thing is that during the phase transition, this m, the energy scale is much larger than Hubble, right? So you can just neglect this the expansion of the universe. And also for the bubble expansion, this beta is also much larger than h. So you can see that this bubble radius, when it collides with each other, typical bubble radius is much smaller than the Hubble size. So in both cases, we can neglect the expansion when we consider the. Yeah. Yeah, so that means, so what as I just argued, we can just neglect the expansion of the universe when we consider the bubble nucleation and collision process, right? And so then we can, in the Minkowski space, we can do right? We can do weak rotations and using the Coleman's method. Yeah, so that's what we did. Okay, so now we can calculate what is typical value for beta. And so the calculation is a little bit long. So yeah, what is the key point is that, so usually the value of beta over h is like 100 in the standard, in the case of, it's like 100 in the case of phase transition happened in radiation domination error. But here it is actually happened during inflation, and during inflation the evolution of the inflaton field is actually very, very slow, right? So then it is suppressed by slower parameter. So in our case, it is also suppressed by slower parameter. So you can see that it is proportional, it's beta over h. It's proportional to these two factors. That is about the standard, like around 100. But it is also proportional to 1 over NE, okay? And this 1 over NE is the number of E-fold, okay? And the typical number of E-fold for the phase transition to happen, and it is also the typical number of E-fold of inflation, right? So it's around something like 60, 10 to 60, something like that. So now you know that the value of beta over h is actually get a little bit suppressed. So the natural value for beta over h for the phase transition, if it happened during inflation, is something like 10. Okay, it's 10-ish. So this number is actually very, very important for later calculation of the gravitational waves, as we can see. So now let's talk about the primary gravitational wave. Okay, so what is a gravitational wave? So we know that, I think everyone learned general relativity, right? So in general relativity, you just write down the metric, okay? You just write, so the space-time structure is described by the metric, and the fluctuation of the metric just gives us the gravitational waves. Right? So we just so in Minkowski space we just expand the metric in this way. But we know that if we're in the expanding universe, it is a little bit different, but it is very similar. So it is the perturbation part of this metric that gives us the gravitational wave. Not only that, we know that the gravitational wave only has 2 degrees freedom. So that is actually the traceless and transverse part of this H, right? This H that is describes the gravitational wave. And so we can just linearize the Einstein equation and to get a wave equation. So in flat space time, it's just like this, okay? It's just a wave equation, and this part is the source is the traceless transverse part of the energy momentum tensor. And but now we are in an expanding universe, right? In the expanding universe, a lot of things are different, but are very similar. So in the expanding universe, what's described the metric is the called the Robertson-Walker metric, right? So you have this part. This is a scaling factor, but it is changing with time. And we assume that the background is homogeneous, right? It's a homogeneous, and so it only depends on time, but does not depend. It's isotropic and homogeneous. In that case, we can just use AT to describe the expansion of the universe. And usually when we study this cosmology, right? So we use conformal time. So what is conformal time? Conformal time is defined in this way. So if we write down the metric in this way, then you can see that this part, space and time, is flat, right? And so the scale factor is here. So then this is conformally flat. So then we call this time the conformal time. But once the relation between the conformal time and the physical time is just like this. As you can see from the transition from these two metrics, the transformation from conformal time and the physical time is just like this. And so we can just do a time integral, right? But once we do a time integral, what we can see is that if the expansion of the universe is accelerating, that means the conformal time has a future event horizon, okay? It has a future event horizon. And we can choose the future event horizon to be tau equal to 0. So that means the time, if we use tau, it evolves, but it stops at some time, okay? And if we use this tau, then what happens? So we can start to solve the wave equation for gravitational waves. And so how to solve gravitational waves? Just like E and M in electrodynamics, right? So in electrodynamics, we solve the electromagnetic wave. So we solve the Maxwell equation. So how to solve Maxwell equation? Is what we solve is we first solve the Green's function, and then we convolute the Green's function with the source, right? Then we can get the electromagnetic wave. But here for GR, for general relativity, it's the same. So we linearize the Einstein equation, and we can get a wave equation. And then we first solve the Green's function. And then we convolute the Green's function with the source. And in this case, the source is the traceless transverse part of the energy of the Einstein equation, right? So then it's like this. So this is a linearized Einstein equation in the theta, okay, or in the expanding universe. So the additional part, so using conformal time. So this prime means the derivative with respect to the conformal time. And you can see that the difference is that there is a friction term, right? So that is the only difference. Oh, so another difference is that the conformal time will have a future event horizon, right? That is super important in our calculation. And so the first step is to calculate the Green's function, right? So now let's calculate the Green's function. And if we do a Fourier transformation, the wave equation is like this, right? It's just a usual wave equation with a friction term and with a delta function source. So the calculation is like this. So we can just do a qualitative calculation. So because we are calculating a Green's function, so the oscillations always start from some fixed time. We call it tau prime, okay? It is tau prime. And then it oscillates, but with this friction term, its amplitude becomes smaller and smaller. But we know that there's a future event horizon at tau equal to 0. So then once it hits this future event horizon, it will just frozen, right? It is frozen. The value of H will frozen onto the future event horizon. Now that's changed. That's for a different mode with a different momentum, right? So it starts at the same point and oscillating, and then it will be frozen on a different value on the event horizon. So that means that HF, as you can just see, the HF just oscillates with the momentum, right? Why it oscillates with momentum? It's because tau prime and the event horizon just fixed, right? So it's like something like similar to a standing wave. But this HF just oscillates with the momentum. But what inflation does for us is that after inflation, the universe just becomes the expansion of the universe is decel. That means all these modes, once frozen onto the horizon, will slowly re-enter the horizon. Once they re-enter the horizon, the modes will oscillate again, right? Once the modes oscillate again, this value of HF will become the amplitude of the wave, okay, of the mode. Instead of what inflation does for us is that inflation erases the information of the phase of HF. Okay, so that's why this HF is very important. So we can see from this cartoon. So here we use the physical time. So what happened for the physical time is that this part is inflation, and this is the end of inflation. This part is the end after inflation. Okay. So what happened is that if we use physical time, as the wave will oscillate, and then frozen. So in physical time, frozen means that its amplitude doesn't change, right? You can see it becomes flat. And then right after inflation, this mode is still outside the horizon, right? Because it is still outside the horizon, it is still flat, right? It is still flat until it re-enters horizon. But once it re-enters horizon, it completely forget about its information of the phase. So they all start to oscillate with the same phase. Okay. So then this HF becomes amplitude, and that's why this then this the mode of the gravitational wave, the amplitude will oscillate with the frequency, and because the amplitude oscillates with the frequency, the energy density also oscillates with the frequency, right? So this is the typical picture for the energy density of the gravitational wave induced by a delta function source, right? A delta function source. But what happened for a real source? For a real source, okay. Yeah, they re-enter the horizon at different time, as you can see like this. Because it's although at a different time, but still there's no information of the phase. So this HF becomes the amplitude. And the energy density will be proportional to the amplitude squared, right? Yeah. Sorry, say again? But it's not, they enter at different times just like this, right? But although they enter at different time, but still you can see that this is amplitude, right? Yeah. Okay, this is amplitude. So yeah, so there is a modulation, but that modulation is not from the phase information here. It's actually only by time. Okay, so there's an oscillating, but you can see that it's not all the same amplitude, right? So this slope, I think this slope is because they enter the horizon at different time. Yeah. Okay. So that does not give us any further information of does not change the oscillating pattern, right? So now what happens is that for all the real source, there's a finite time duration, right? And for the finite time duration, it will smear this oscillating feature, right? So for example, in the case of what we studied, the first order phase transition. So for the first order phase transition to complete, we know that this beta must be much larger than h. So that means there's a beta inverse, which is a typical time scale, should be much smaller than h. Should be much smaller than h inverse, right? The Hubble time. So that means that it can only erase the oscillating pattern in the deep UV part, right? But not for the whole parts. So for the modes with the physical momentum between h and beta, we still expect there should be some oscillating pattern. So this multi-peak feature is the typical feature for gravitational waves from phase transition during inflation. Okay. And so what is the size? This is a slide. Okay. So what is the size of the gravitational wave? That is also important because we always have the impression that everything that goes during inflation should be diluted, right, by the inflation of the universe. So now let's count the redshift. So So how to consider the size of the gravitational wave? We need to consider it with the size of the radiation, right? Because today the radiation we can observe, it is about 10 to the minus 5 times the total energy density of our universe, right? So we can just compare the energy density of gravitational wave to the energy density of radiation. So what happened is that during inflation, all the energy of the density of today's radiation was stored in the inflaton potential, right? And so during inflation, the inflaton potential actually doesn't change. So during inflation, it doesn't redshift. But the gravitational wave, once they produced, they were inside the horizon, okay? Because they were inside the horizon, they just behave as radiation. So we know that radiation redshifts as a to the minus 4th. A is the scale factor, right? And so this is it's produced, and so later this gravitational wave will evolve outside the horizon. Once they evolve outside the horizon, its amplitude doesn't change, but its frequency still shifts. So then it redshifts as a to the minus second power, right? But at this time, the total energy density of the universe, that is the later radiation energy density, is still inside this gravitational potential, so it doesn't redshift. So, but after inflation, what happened is that this total energy density of the inflaton field will soon become radiation, right? Very soon become radiation after reheating, and so then it starts to redshift as a to the minus 4th power. But this gravitational wave, it is still outside the horizon, right? So it redshifts as a to the minus 2nd power. And once this gravitational wave re-enters the horizon, both of them, right, redshifts at a to the minus 4th. And what happened, ironically, is that this part, this 2 a to the minus 2, and this a to the 0th power and a to the minus 4th power, they just cancel with each other. So these 4 parts are the same. That means the only additional redshifts, because the only additional redshifts induced by inflation, right? For the fact that the phase transition happened during inflation, is only when it's only between the production of the gravitational wave and this and the time it evolved outside the horizon. Okay, so this is the only additional redshifts, and for the typical wavelength of the typical wavelength of gravitational wave, it is actually determined by beta. Okay, and the horizon size is Hubble. Okay, and so that means that the only additional redshifts is determined by this power. Okay, it's this h over beta to the 4th power. That is the only additional redshifts. Okay, so what is the size? So typically for gravitational wave from the phase transition, it is usually proportional to omega r, which is the total energy density of radiation, times h over beta to the 2nd power. Okay, and now because it's happened during inflation, so there will be additional 4 powers, right? So the story is like this. So this is the gravitational wave spectrum, right, for phase transition, if it is produced in radiation domination or in flat space time. So there's an IR part and there's a UV part. And what happened for the phase transition during inflation is that, so what inflation does is that it just distorts this spectrum. So it distorts this IR part into a new IR part with a oscillatory part. And it squeezed this model-dependent UV part into a new UV part, right? So in some sense, the spectrum is kind of universal. And the size for here, right? So this is a peak, right? It squeezed this peak here. And this peak used to be h over beta to the 2nd power. But with the additional suppression from this from the redshift during inflation, so then it has the additional 4th power of h over beta. So now it becomes h over beta to the 6th power. And also we should assume that the latent heat released during inflation should not be very large, right? Should not be large compared to the total energy density of the universe during inflation. So then it should also be suppressed by delta rho over rho inflation, and this delta rho is the latent heat density, and this rho inflation is the total energy density of the universe. So it will be also suppressed by this factor, and so, but this is not for the peak. For the peak, it's actually different. So the 6th power becomes the 5th power if you do a more careful calculation. So it is a little bit larger. Okay. So then the typical size of the peak value of the gravitational wave produced during inflation can be given by this number. It's omega r times h over beta to the 5th power times delta over rho to the 2nd power. So if we are lucky enough, if these two values are not very small, know that omega r is something like 10 to the minus 5, right? And if this h over beta is something like 0.1, and if delta rho over rho is also 0.1, then this number, this omega GW is 10 to the minus 12. Okay, and 10 to the minus 12 can be is the value that can be observed by most of the future gravitational wave detectors. But if we are very unlucky, right, then if this h over beta is super small, like it is only 1%, then this value of omega GW is something like 10 to the minus 17. Then we cannot just observe it in the. It will be hard to observe it in the near future. Okay, so what is the frequency? Frequency is also very important, right? So the frequency is, as we can see that this peak, the physical value of this peak, right, when the gravitational wave is produced, is actually the size of the Hubble, okay? And so what is the frequency today? What we just need is to count the redshifts. And there are two sources for the redshift. So one is the redshift during inflation, and the other is the redshift after inflation. And for after inflation, it just redshifts as the Europhoton, right? We just compare the reheating temperature to today's temperature of the SAM-B, right? So that is actually fixed. But what is not fixed is the redshift during inflation. Because the redshift during inflation is strongly dependent on the value of NE. And NE is the number of efforts before the end of inflation, right? For the phase transition to happen. So this is some typical benchmark values. So for example, if we assume that H inflation is something like 10 to the 12 GeV, and if delta rho or rho is something like 30%, right? And now if the phase transition happened about 38 efforts before the end of inflation, then the frequency is just like around nanohertz and can be observed by the pulsar timing array gravitational wave detection method. And if it is about if NE is about 25 or 21, then this value of today's gravitational wave, the frequency of today's gravitational wave fall into this region, and it can be observed by future space gravitational wave telescopes. And if it is something like 15, then its frequency is in the range of future terrestrial gravitational wave detectors. Yeah, so there's some typical value. So I think now everyone's a little bit tired, so we can just move gear to dark matter, and I will just give a very brief description. So this is actually very easy. So because when I gave this talk like a few years ago, so one student asked a question, Xitong asked me a question. So what happened for the energy density released during the phase transition, right? So and then I have a joke with it. So if this is symmetry restoration, right, then the particles produced after the Barbour collision can be stable. And that can be a source of dark matter, right? Can be a candidate of dark matter. And then so later we wrote a paper together. So basically we assume the symmetry restoration phase transition, and we calculate the energy density, and we count all the redshifts. And so in some parameter regions, we can have both the gravitational wave, detectable gravitational wave, and the today's observed dark matter radical abundance, right? So that is some details. So I will not go talk too much about it. So another thing is the curvature perturbation, right? We know that there must be curvature perturbation. The reason is that there must be a curvature perturbation. The reason is that we assume a direct interaction between this inflaton sector and the phase transition sector. Because there's an interaction, right? So that means it is a potential. There's a potential interaction. V depends on both phi and sigma. So we can just do a tighter expansion of V, right, over this phi. So we can just do this kind of expansion. So now you can see this is partial V1 over partial phi 0. This factor just involve the spectator field innate. And it can be seen as the source of delta phi. And we know that a large part of the curvature perturbation is actually contributed by delta phi, right? So that the phase transition through this kind of interaction will become a source of the curvature perturbation. So we can write down the equation of motion for delta phi, right? So this is the Euro part, and this is the source. And actually the source in this case composed by two parts. One is through the direct interaction, and the other part is pure gravitational. And in our case, since we already assume there's a direct interaction, so we can imagine that the gravitational part is actually small, subdominant, right, compared to the direct interaction. So what we need to do is to simulate the source. The reason is that this source is different from the energy momentum tensor, right? So people has never done that before. So what we did is that we do some numerical simulation. So we just numerically. So we just randomly generate bubbles, and then we put this nucleated bubbles into this lattice, into a 1,000 cubic lattice, and then we let it evolve just by solving this partial differential equations on the lattice, right? So it's a very simple, much simpler than what Professor Wang just described. And so we solve it, and then it becomes a source. And then we can easily calculate the Green's function for delta phi, and then we convolute the Green's function together with the source. We can calculate the configuration of delta phi. We can calculate delta phi. And then from delta phi, we can calculate this curvature perturbation. And then, so this is actually the power spectrum of the curvature perturbation, and in the case of very large beta, okay? And in the case of very large beta. So, yeah. So once we get this curvature perturbation, we can calculate the 2-point spectrum. And it turns out we can just fit in the case of large beta over H, we can just H over beta. In the case of large H over beta, so H over beta is like 0.2, right? We can it can be like described pretty well with this empirical formula. So we can just calculate the empirical formula, and this spectrum can be parameterized by 2 parameters. So one is the amplitude, and the other is the frequency, right? And this shape function is actually almost fixed. Okay, so it can be the amplitude and the center frequency. They are the 2 free parameters determined by the phase transition, by the details of the phase transition. So then, once we have this power spectrum of the curvature perturbation, we can use it to calculate a lot of things, right? First, we can calculate large-scale structures, but this is actually ongoing work. So it's like this. So once we tune this HA over beta to be very small, then we know that this induced curvature perturbation can actually be small. It can be as small as the quantumly induced curvature perturbation during inflation, right? And so if the phase transition happened about 60 e-folds before the end of inflation, then we know that all this information can be printed on the CMB spectrum, right? So that means maybe we can by future more accurate CMB detections, or maybe future 21 centimeter detections, observations, we can just see this kind of fluctuations, right? And we can know if there's a phase transition happened or not. So this is a work in progress. And another thing is a secondary gravitational wave. We know that if the curvature perturbation is large enough, right? So once it re-enters horizon, the curvature perturbations just become the gravitational potential. And if we expand the Einstein equation to the second order, the gravitational potential itself can become a source for the gravitational wave. And this is a standard calculation. People have done that for a long time. And in our case, since we already have the spectrum, we already have a simulation for the curvature perturbation, we can just put it into the source term, right? And then convolute it as the Green's function, and to calculate this gravitational wave, the secondary gravitational wave today. And it turned out that we did this calculation, and it turned out that the IR part of the spectrum is actually universal, and the UV part drops very fast. So that part is model dependent, but it's not very important. So we can give an analytical formula of this IR part of the spectrum. It's like this. So this X is actually the frequency. So the gravitational wave, secondary gravitational wave spectrum is like this. You can see. You can see it also determines by 2 parameters. So one is this one, this amplitude, and the other is the shape function, right? But the shape function is actually the frequency in the shape function is actually determined by the peak. So there's only one free parameter, which is the frequency at the peak value. Okay, the frequency at the peak value. So there are 2 parameters. One is A reference, the other is F reference, and the F reference is actually determined by NE, okay? So NE is the most important. So that the redshift during inflation determines the frequency, okay, of the gravitational wave. And the important part is that, so last year, so all these 4 pulsar timing array collaborations released their results. And all of them claim that they see this Haipeng curve, right? We know that Haipeng curve is the signature of the gravitational wave, right? So stochastic gravitational wave background. And for nanograv, since they already accumulated data for a long time, they even published the gravitational wave spectrum. Because they published gravitational wave spectrum, what it gave us is something like this, right? You can see that the IR slope of the spectrum actually gives a lot of information. So the slope is around 2, right? It is actually different from the gravitational wave from phase transitions. So usually for gravitational wave directly from first order phase transitions, this slope is about 3, okay? But here in our case, we are not, the dependence in the IR part is not only 3, but it also proportional to all these kind of log factors. And these logarithmic factors are from the transfer functions, because for the curvature perturbation to produce gravitational wave, it will first re-enter the horizon, okay, re-enter the horizon, and then produce gravitational wave. So in that case, the transfer functions just come in, and we have more structures of gravitational wave. And so with these more structures, we can just give a very nice fit of the gravitation of the observed nanograv spectrum. So with the tools provided by nanograv collaboration, we can even calculate the Bayes factor. So this is a Bayes factor against the supermassive black hole binary model. Okay, so used in their paper. So you can see that these are the Bayes factor for different new physics models, and actually our model gives currently the best fit, right? And yes, currently gives the best fit. So these are the two benchmark points we choose in this plot, and so you can see that here this is the prediction of this two benchmark points. You can see that it can fit this IR part pretty well, and for the UV part, actually people doesn't really know what really happens because error bar is super huge, right? Yeah. So we can have a little bit of comparison for the primary and secondary gravitational waves. So the primary gravitational waves are actually proportional to h over beta to the 5th power and delta rho over rho to the 2nd power. But for the secondary gravitational wave, it is even more surprised by these factors. But it is actually enhanced by the slow parameter. Why is it enhanced by the slow parameter? There's actually a reason. So because all the curvature perturbation compared to the gravitational waves are induced parameter. And here the secondary gravitational wave is actually gravitational wave induced by curvature perturbation. So there's this enhancement of this factor, right? So then you can imagine that in some region of the parameter space, when these two factors are not very small, then this enhancement can make the secondary gravitational wave more important than the primary one. Okay, so now let's talk about the primary primordial black holes. Primordial black holes can be a very important constraint to the secondary gravitational wave, right? Okay, so that's because if the curvature perturbation is large enough, if it is so large, right, can produce a lot of primordial black holes, and that can be excluded. For example, in this plot, this dashed dot dashed line is actually the constraint from primordial black holes, and this part is actually excluded. You can see that to fit this spectrum, actually we need to choose the value very close to the boundary. Okay. Yeah. So in our case, this is also work in progress. In our case, because this curvature perturbation is produced through bubble collisions, that is a classical process, right? For classical process, we know that the energy must be conserved, right? Energy must be conserved. So we cannot expect a Gaussian distribution of the field value. So there must be a very large non-Gaussianity. So this is the result of our simulation. You can see that it has a spectrum, but has a very sharp cutoff. So this is the reason of energy conservation, okay? And so because it is non-Gaussian, so a lot of predictions of primordial black holes calculations just doesn't work, right? So we need to recalculate the bound from primordial black holes. So this is ongoing work. And so in maybe 1 minute, let me talk about topological defects. So this is mainly for secondary gravitational wave, second order phase transitions. So for first order phase transition, if it's symmetry breaking, it also can produce domain walls, but that is not for this work. For this work, what we consider is secondary gravitational, second order phase transition, and we consider it's a spontaneous broken of C2 symmetry, so that domain walls can be produced. And So what happened is that what we assume is a Landau-Ginzburg type, and so we assume this sigma can be in general can be seen as an order parameter, right? And so its mass square is flipped by the evolution of the inflaton field, just like this. And so the size of the structure is actually determined by the so-called Kibble-Zurich mechanism. Okay, and so what we did is the following. So during the phase transition, so temporarily the mass square of the spectator field becomes negative. And if it becomes negative, then the quantum fluctuation just grows techonically, right? And because it grows techonically, the occupation number of the long wavelength modes, the tachonic modes, are just become very, very large, right? So this is the growth of the occupation number. This F is proportional to the occupation number. So because it becomes very large. But later, when the sigma square becomes large, because the occupation number is large, then the sigma square is large, right? Then the nonlinear effect becomes important. So then the tachonic growth just stopped, right? When the tachonic growth stopped, because the occupation is already very large, then we can treat the field classically, right? So then what we can do is that we can use a classical ensemble to mimic the quantum ensemble. And then through this classical ensemble, we can randomly generate the initial conditions for the sigma k, which is the canonical coordinate, and pi k is the corresponding canonical momentum. And then once we generate them, we can just put them into the differential equation. So put them into the lattice and to do the evolution, right? And so this is the result of the evolution. So we can simulate the evolution of the configuration of the field. So at the beginning, it looks like this. You can see there are a lot of fluctuations. But during the inflation of the universe, there is a Hubble friction. And the Hubble friction will erase will slowly erase all these, actually very fast, erase all these small fluctuations. And in the end, the only structure left is the wall structure. So you can see that during inflation, the walls cannot form a network. What it forms is a static configuration, okay? And so even a static, so let me skip this page. So during inflation, even a static configuration can just radiate, right? So why is that? Because we know that in flat space, in Minkowski space, a static configuration cannot radiate. That is because of energy momentum conservation, right? But during inflation, because of the expansion of the universe, the time translation symmetry is badly broken, right? So that means that even a static configuration can just radiate. So this is what happens. So you can see that the gravitational wave can be written as a kernel convolute with the source. Kernel is something like a Green's function, but with some additional factors. But in the flat space time, the kernel is like sine function or cosine function. And when you integrate with time for a very long time, it just cancels, right? So that's why that is the reason of energy conservation. But here, because it's broken, so we can see that the kernel is like this. So the most contribution is actually from the last peak, okay? And so when the certain mode is about to evolve outside the horizon. And so that's why it can give just non-trivial contribution to gravitational waves. And here we just like the first order phase transition. So once we have this HF, we can start to calculate the energy density of this gravitational waves. And so here you can see there are a lot of curves. Actually, we also did this study for the first order phase transition. So you can see different patterns, right? The reason is that we can assume different intermediate stage between the inflation and the reheating, right? So if there's a short matter domination between inflation and reheating, then the gravitational wave can be smaller. And if there's a kinetic domination then the gravitational wave can be larger, okay, today. And also it will change the shape of the spectrum. So here for second order phase transition, you cannot see the oscillatory feature, right? Why there's no oscillatory feature? Because the domain walls, once produced, they will last a very long time, right? So if you don't give it a mechanism for the domain wall to disappear, it will be there forever. So that means it is not an instantaneous source. And it means that all the oscillatory feature will be erased, right? Just as what is seen here. Okay, so here's a summary. So I hope that I can convince you that because of the large excursion of the inflaton field during inflation, so it will trigger, it is very probable to trigger a phase transition in the spectator sector. And so this might be a common a common phenomenon, right, for the phase transition to have a phase transition during inflation. And so that will give us a very rich phenomenon. So first of all, it will give us primary gravitational waves, dark matter, topological defects, and curvature perturbation, and curvature perturbation will induce secondary gravitational waves, and then we can use it to explain the signal observed by pulsar timing array experiments, and then it can give us large-scale structures and primordial black holes. Yes, and that's it. Thank you.
Can have several questions.
So regarding this uncertainty of the reheating phase, I think one thing that came to mind is you can put an upper bound on the duration of reheating, I guess, because you can put an upper bound on the duration of reheating, I think, because
the upper bound on the duration.
Because you know,
yes.
Well, you know that the phase transition happened, right? So you know the inflaton at least couples to that field that did the phase transition, and if you calculate the phase transition, then you need to specify the value of that coupling. And then you can say, if you only have that coupling, then you know how fast reheating happens. You could just see how fast it happens. In reality, it might happen faster because it might have additional interactions. But I think you can put an upper bound on the duration of reheating by just considering the coupling that you use to calculate the phase transition. You see what I mean?
Sorry, if I understand correctly, you say.
So you know at least one inflaton coupling, right? Because inflaton couples to the field that does the phase transition, right?
Sorry, maybe you don't use the mic. Yeah, that would be better. If you don't use the microphone, I can hear you better. Yes.
So you know at least one inflaton coupling.
Yes.
Maybe it has other couplings.
Yes.
You know this one.
Yes.
So you can calculate
the reheating.
The rate of reheating.
Yes.
Coupling, right?
Yes.
So you know reheating will for sure not take longer than it would take to reheat the universe with that coupling alone.
Yes.
So therefore, I think this uncertainty called the duration of reheating you can systematically minimize. You can put an upper bound on this uncertainty, right?
Yes. I think you're right. Yes. So we can just So in our calculation, we didn't consider detailed model for I think you're right. So because we already have the sigma field, right? So we can calculate the reheating through this sigma field. Yes, exactly. Yes, I think that is a good point. Yes. So we can just calculate because there's oscillation, right? You can expect some like a preheating phase, right? Yes. Okay. Thank you.
Yes. So can you explain a little bit more how dark matter is produced and how it's related with the phase transition?
Yeah. So that is dark matter is produced during this one. Yes. So because we assume there's a phase transition, right? And we assume the phase transition is symmetry restoration. So that means the phase transition is from here to here, right? And so here you have because it is a symmetric phase. So and because the bubble collision will induce some sigma particles, right? And in the symmetric phase, sigma particles is stable. And so you produce a lot of sigma particles. So here we assume that the total energy density of the latent heat density is about 10% of the total energy density of the universe, right? So that is actually a lot. Because today's dark matter is only about, let me see. So if we assume that the dark matter mass is about the proton mass, right? We know its number density is super small, right? So then if the dilution is not super large, because here the energy density is large enough, right? We can stand the 10 to the minus 10 dilution. And 10 to the minus 10 is something like, you need to take 1/3 power of it, right? So it's something like 10 to the minus 3.3, right? And 10 to the minus 3.3 is something like e to the minus 10, right? So if the phase transition happened about 10 e-folds, between 10 e-folds before the end of inflation, then the dilution can be just okay to produce today's dark matter, radical valence.
Okay, do we have other questions? If no, let's thank Professor again.